let's take a look at a few examples of applying normal distribution. So when you take a look at the normal distribution, so you have this nice bell curve. Okay, so I introduced these topics. I'll put up a video up above there in case you want to go over that. In this video, I'm just going to tackle the examples, so several examples, and I'm going to try to show you how to approach and calculate probabilities from this normal distribution. So it is a probability density function. So how do you do that? There's different ways. You can do it by, if you're lucky enough, if you're being asked about probabilities with respect to some standard deviations, then it's much easier. You can use the standard, kind of this particular bell curve where those numbers, within one standard deviation, about 68% of the data lies and so on. Another way is that you can convert, so going back from your regular mean and standard deviation, you can find out what the z-score is, and there are actually tables that are listed, so they're pre-calculated because they're just so often used, so we can do that. And then of course the most used now, especially as you kind of start leaving school and then maybe doing research or doing stuff on your own, you're very, very rarely are going to be calculating things through tables or just kind of guessing. You can certainly use a graphing tools. So I utilize Desmos. And then I will, on one of the occasions, let's say if you're stuck and you're on a test, and then really your teacher really wants to push you. So, how would you approximate if what you're trying to calculate doesn't really fall exactly on the standard deviations you want? Maybe it's a little bit off. So how do we do that? How do we approximate that area? Okay, so I'm going to show you that. And then, so that utilizes, as long as we kind of recall our function. So for the normal distribution, which is shown right here, if we have that, we can actually approximate anything that we like. So let's jump into several examples. All right. So here's example number 1. So it turns out that height in the population is actually normally distributed. Okay, so we have seen that. Okay, through the various statistics, it has been documented that the average woman's height in the U.S. is about 64.5 inches. So if you recall, okay, so it's about 12 inches, okay, per 1 foot. So you can certainly convert this. So it's about 5 feet and about 4.5 inches in terms of a mean. And then our standard deviation, it says it's 2.5 inches. So that is something that we're gonna have to utilize. So let's highlight these couple of things for ourselves. So here is our mean, here's our standard deviation. So I'm going to just write down these things. So here's the given pieces of information. So I'm going to assume that the mean, okay, is 64.5 inches, and then the standard deviation is 2.5 inches. So that's what we have there. What is the probability that when you walk into your first year, let's say post-secondary class, the first female will be taller than 67 inches. So what you really want is you want to find out the probability, all right, that you are, I guess, taller. So that means, you have something taller than 67 inches. Okay, so how would we calculate this? Well, the first thing that you may want to check, because you do have your standard deviation, notice that actually your mean, so 64.5 plus your standard deviation is actually 67. So what you have, so you don't even have to calculate much in here. So this example is very forgiving. I won't even need the top one there. I'm going to just copy this. Okay, so right here, I'm going to put it down here and then just shrink it so that we can see it. At the top, I don't really need right here. So we are 64.5, that's our mean, and we're basically, what we're trying to do is that it's, we're greater, okay, than 1 standard deviation, which would have been, this is at 67 inches. So we want to find this area under the curve. So that's actually pretty good. You know, we can certainly do that because we know exactly what that is. So if you can see this and you have this bell curve with you and you still remember these numbers, then this is great. So the probability would have been equal to, so I can just sum up the probability. So this would have been 13, let's say, okay, 0.59% plus 2.14%, and then, you know, plus that little tiny, okay, percentage there. So that would have been the probability. So I can sum up these things. We swing this over, 13.59. Now, of course, it is just approximated, 2.14, and then plus 0.14. All right, so the probability is actually small to have someone that tall, okay, if you were going to see them. Now, you're going to, of course, see people who are taller than this, okay, but that's, you know, you're assuming that you're taking the entire population and you're walking around. But this is just saying that on our first, you know, the first student that we would see, okay, who was a female, would have been taller than 67 inches. So that's one way that we could have calculated this, okay, based on the normal distribution. Now, of course, you know, we can, so I'm going to go back, I'll show you another way. So let's bring up Desmos. Okay, so this is going to be something we can calculate. I'm going to go up to the functions, and so this is normal distribution. So we have 64.5, so we're going to be entering our mean and then our standard deviation so that it gives us our curve. All right, oops, this is not what we wanted here. Okay, there it is. Okay, so we're around there. Okay, and 67. So yes, we do want, okay, so notice just below it, it says cumulative. I want to have a cumulative, but okay, the minimum is going to be 67. So it goes from 67 all the way in, and then, so it highlights that for us. Desmos does, and then it shows us, so 0.1586, okay, so on, so approximately, you know, 15.86 or 87%, which notice that if we use this is exactly what we got, 15.87%. So you can use the bell curve itself to be able to calculate it. If you have a tool like Desmos, then great. Okay, so that's the first example. It's a simpler example that we have because it just fell under the standard deviation. So let's see another example. Okay, so here's another example right here. So it says the average IQ, so intelligence score, is normally distributed and in the adult population is about 100 with a standard deviation of 15. Now, it is asking us what is the probability that at a party the first person you speak with will have an IQ of no more than 120. Okay, so that's fine. So let's write down these things. So what do we have? We have our mean, okay, which is at 100. We have our standard deviation, which is actually pretty big, it's 15. And we want the probability, and now this is no more than 120. Okay, so x, okay, so it's not greater, no more. So we have no more than 120. Now, notice that it doesn't actually matter, okay, if you include 120 or you don't include 120 when you're doing these continuous probability distributions, because of one particular point, okay, it won't matter. So these, okay, so if you write it, you know, like this, these are actually equivalent, all right? Okay, so that is that. So that is just because it's continuous probability distributions. So this is what we want to find. So how would we do this? Now, 120, okay, so notice what's going to happen. Our standard deviation is 15, so that's 100. So we know that we're going to be, you know, we're shifting over more than one standard deviation. So it's going to be a little bit more than one standard deviation. It's actually 5, so about one standard deviation and a third. So using something like this, that we have in here. So let's see if it still remembers. I'm going to just paste this up here. Okay, good. Okay, so using something like this, it's fine. You know, we can start approximating this. So I'm going to just, we can certainly do that. Now I don't need, okay, all of this in here. I actually will need, okay, this either. Okay, so let's simplify this. Now, where are we on this? So our mean is 100, right? This is one standard deviation is going to be 115, but we're at 120, you know, so second standard deviation, so 2 standard deviations away would have been 130. So actually, as you can see, having IQs as you keep going, you know, 130 or above, so it's only about 2% of the population that have that. So we're somewhere along here. So we're stuck, you know what, somewhere along here. So we're supposed to be 120, right? Okay. So we're stuck at somewhere along here. So this is what we want. Now, we want to know what is the probability that at a party, the first person you speak with will have an IQ of no more. So, okay, well, no more, so that means, you know, we have to fill up all of this. So we have to know, all right, so we have to find the area under the curve. Now, finding the area under the curve up to the first standard deviation is fine. So that's not very hard to do, right? So we can just sum up everything, okay, to the left. But it is this little piece that actually is annoying. So this little piece right here, so that's the piece that we are kind of stuck with. So we're going from here to about 120. All right, so this is from 115 to 120, you know, and it's falling, okay, something like that. Now I'm going to do this, I'm going to approximate it, okay? So we're going to try to do this in several different ways just to show you. So how would I approach and find this probability? Let's say that this was a test, and now you have nothing given. Say you don't even have graphing calculators. Most of the time you will now in statistics, so you can literally use something like decimals or your graphing calculator. But say someone wanted you to find out, okay, what this actually is in terms of an approximation. So what I recommend, okay, in these instances, you know, you can certainly use, okay, so to the left of one standard deviation, we know what that is. So the probability would be, so notice it's 68.26%, right? So that's within that one standard deviation. Now to the left, all right, so on the negative side, or to the left of the, okay, so going in this direction right here, you know, we just calculate it. So that's just this plus that, which we just did, which was 15.87, I believe. Yeah. So 15.87. So this is going to be 15.87. And now it's going to be plus, you know, this little piece that we need to know. But it's an exponential. So, you know, how do you calculate the exponential area under the curve? You can certainly approximate it. So, you know, if you do this, you know, let's say if I approximate this, okay, and I assume that this is just a straight line, as it is, right? I can find the area under the curve here of this. You know, it's a rectangle and a triangle. And I actually did this type, okay, of approximation when I was talking about exponential distributions. You know, I'll put up a link up above there, you know, and that I did a detailed one. And, you know, you can take this point and this point. Now, if it's on a test or in a quiz, what I actually recommend, and this is what's done normally, is instead of just doing this, we typically will just take the midpoint, which is exactly the area, okay, there. So we just want to know the midpoint. So we want to know what this height is. Now, the base we know is 5. So what's the height of the midpoint there? Well, the midpoint, okay, would have been, so we can take, okay, so this right here, you know, so let me copy this down for us. So that's the function, right, of the normal distribution across, where we know the standard deviation, we know the mean. So we can say that the midpoint, so here, I guess that would have been, what, 117.5. So that would have been our x value that we would have substituted here. And then once we have, so once I substitute that in, I'll get a value. So I'll know what the height here is. I'll know what the base here is. So I can find the area under the curve, and I can, plunk it into here and then add it all up, okay, to get the total sum. So that would have been kind of the approximated. It's not going to be exactly, but we'll do it also on decimals just to kind of double check. So let me substitute this in here. I'll do it in fast forward fashion. All right, so here we go. So here's the midpoint, I guess the y value, or the f at 117.5 value. Now if we take that and then we multiply it by 5, which is the base. So if I multiply this by 5, so it's going to give us approximately, let's say, 6.73%. Okay, so 6.73%. Again, because you're just approximating this, it's not going to be perfect, but it should be good enough to get a good sense of what the probability for this particular example would be. So I'm going to just substitute all of this in. 6.7, say 3. So it looks like you have, I don't know, let's round this off. So about 90.9% or 91% probability that you're going to meet someone with an IQ of less than, or I guess equal to 120, so approximately that. Now, what if we used decimals just to double check this? So I can go back into decimals. So I'm gonna change this around here. All right, so here you go. So I just substituted it in. I put in the mean, the standard deviation, and then notice the cumulative probability, which it calculates. So to the left of 120 on the IQ, notice 0.908788 and so on, and we got in our calculations, actually, what was it here? No, so there you go, 90.893, which is not very far off. So our approximation was actually really good, okay, for this one. Okay, so you can do it by hand. If you have the tools, then amazing. So that's you can certainly do that. Now that was another example, and now you've seen you can see decimals, you can see how to use the bell curve, you can see how you can approximate. Now you can do a better approximations by dividing it into smaller pieces. So we could have taken this, so it's something like this, and then this is, so you can do it let's say into two pieces, and then calculate the area under the curve for one piece, and then calculate the area under the curve under the other piece. So the more pieces you put in there, and so those rectangles, the better your approximation will be. But you can see, this approximation was already pretty good. So that's not bad. So that was this particular example. Here's a last example. So this is actually with birth weights, and birth weights are normally distributed as well. So you have heights, you have IQs, so a lot of things in the population will be that way. And this is for humans, but you can be dealing with bacteria and viruses, and then so you can approximate things by normal distribution there as well. So now here it says your aunt is to give birth in the coming month. So the birth weights are normally distributed. So it looks like on average, at least for this example, it says 3.5 kilograms is the mean, and then the standard deviation is 385 grams. So just be careful so that the units are consistent here when you're changing it up. So I guess, we can change everything to grams, or we can change everything to kilograms. What is the probability that the baby will be born with a mass of at least 3 kilograms? Okay. Put it into, I don't know, into grams. So 3500, so that would have been our mean. 385, okay, is our standard deviation. So now we want it at 3000. So what is that going to be? How many standard deviations away? Well, it's going to be more than 1, but it's going to be now to the left. So we have 3500 minus 385. So this is 3115 right here. Answer minus 385. Another standard deviations. This is 2730. So 3 kilograms. So we're basically, stuck somewhere, somewhere over here. Now I'm not going to use the method that I used before. I want to show you another method. So you can use decimals. You can use, directly, okay, the approximation. So here we could have approximated, okay, so basically you can take all the way up to, you can take the area, moving in this direction all the way up to here, and then you can subtract this piece right here. You can subtract this one away and then get the sum to the left, or, you can take it up to this point and then approximate this piece right here. So, we could have done that by hand as we did in the previous example. So now in this example, I want to show you a completely different way, which is also used. And that is converting things back into z-scores. So when you convert things back to a z-score, it changes the mean for you to be moved to 0, and then your standard deviation to be moved to 1. Clearly, that's not what we have. But when you are doing this transformation, okay, in the computation of z-scores, it's actually nice, okay, if you do that. So our z-score, so this would have been, whatever value you're looking for, so minus your mean. So this is, how many standard deviations we are away. So here's our z-score. So for this one, we have 3000 minus the mean, which is 3500. And then standard deviation is 385, right? Yeah. Okay, so I'm going to just show you, let's calculate what this is, and then how to use and what to do with this z-score. So I should have known that. Answer divided by 385. So we are negative 1.2987 approximately. All right. How many standard deviations we are away. And what this does, all right, so if I remove this, now it has a mean of 0. So when you calculate this, okay, and you get this score, and what it's saying is that you are negative 1.29 away, so basically, so this point is negative 1.2987. And I might say, okay, so what? Well, what you want is, you want to know the area under the curve, okay, to the left of here. And what we use, and this is, you can look it up on the net, you'll find this, okay, so I have actually, so this is on math.arizona.edu, okay, website, and it actually gives you a z-score value. So for the normalized, so the standard normal distribution, and notice it has your z-score on the left, okay, and then you can find the probabilities. Now these probabilities are to the area on the left hand side. So what are we searching for? Negative 0.2987, okay, so that's what we want, negative 2987. So we're gonna go, so negative 2, okay, so we are, okay, right here. Let me, because I copied this into, okay, so right here, so I can highlight this so you can see. So negative 29, so right here. All right, so we have that. And then on this scale, so negative 29, so notice, okay, on top here, it has these values. So we want negative 29, sorry, I forget what it was. 2987. So to be honest with you, it's about negative 1.3. Okay, so that is the z-score. So if I do that, so negative 3 right here. Okay, so this is going to be, okay, our probabilities, okay, for that. So approximately, 0.0968, so about 9.68%. All right, so that's what we would have had, 9.68%. So I just looked it up from the table. So this is utilizing z-score tables for the standard normal distribution. So 9.68%, that would have been the probability, okay, to the left of the curve. Now, again, if I pull up Desmos in here, so if I pull Desmos back up, let me change this. This is 3500, 385, and I was looking for, this was 3,000, and there you have it. So about 9.7%, right? Which is the probability, okay, that you see there, and exactly what we got, 9.68, which is about 9.7, right? Again, because I rounded this to negative 1.3, it's a little bit bigger than that. So you have now seen several examples with these normal distributions. And again, you can either have this nice table, and sometimes teachers might give you this table, or you have it at the back of a book, okay, of your statistics book, and then you can look up through this table the areas under the curve, so you don't have to compute them. You can do that. You can use Desmos, you can use a graphing calculator if you're allowed to use those. You can do it by hand, okay, as I've shown you, because you're just approximating things out. So that brings us towards the end of these examples. So I hope that these 3 examples would give you a glance and make you understand how to use these normal distributions to find probabilities. They also can be, not to the left or to the right. They can be within a range. You can do that as well. All right, thanks for watching. We'll see you in a future video. Bye, everybody.